Overview. In my previous article, you learned about Docker containers as a tool to bundle your application with its environment and dependencies. The next step in building a scalable web application is to deploy your container to the cloud. But it isn't sufficient to just deploy the single container, you will also need to specify how the scaling of that container will take place. What is container orchestration? To manage to scale, spinning up new container instances and shutting them down as they are no longer needed, you will use a container orchestration service. In addition to the auto-scaling of containers, the orchestration service helps balance loads, check health, and manage the container's lifecycle, instantiating, scaling on multiple hosts, configuring, networking, and much more. There are several tools for orchestrating containers, and in this article, we will focus on Kubernetes. Container scaling. 1. Vertical scaling. Increasing the host machine's hardware resources on which the container is running is called vertical scaling. This approach's downside is that it is challenging to scale up or down as the demand changes automatically. Larger host machines can be more expensive than smaller machines, so it is a loss if the machine is underutilized. Also, running an application in a single container alone doesn't leverage the full power of containerization. 2. Horizontal scaling. Running multiple instances of the same application across multiple machines is called horizontal scaling. Why is Kubernetes required? In my last article, you learned to containerize your application. The containers that you created were running locally on your machine. There are limitations to containerizing applications locally, such as 1. Scaling. You cannot automatically scale up or down the resources, number of containers, or application usage requirements based on the incoming traffic. 2. Updates. Assume you have manually scaled up your containers horizontally on multiple hosts. Now, develop a patch/update in your application. It will be difficult for you to update the patch in each container manually. The solution to auto-scaling problems number 1 and 2 above is to use Kubernetes. What is Kubernetes? Kubernetes is one of the most popular orchestration systems for containers developed by Google and open-sourced in 2014. It can automate many of the manual operations of deployment and scaling of a containerized application. A few of the benefits of using Kubernetes, K8s, are the ease of scaling the container instances up or down to meet varying demands, horizontal scaling. It can balance loads, and perform health checks. It helps in setting up inter-container communication, networking. Container health management. Rich ecosystem. Secrets and configuration management. The downside of these features is the high complexity and learning curve of Kubernetes. Key terms. Cluster, a group of machines running Kubernetes. Master, the system which controls a Kubernetes cluster. You will typically interact with the master when you communicate with a cluster. The master includes an API, scheduler, and management daemon. Nodes, the machines in a cluster. These can be virtual, physical, or a combination of both. Pods, it is considered the smallest unit in a cluster. It is a logical group of containers on a node that runs a particular module/application. A pod consists of one or more containers, shared storage resources, and a unique IP address. Note that all the containers within a pod share the namespaces and file system volumes. Pods are not persistent and may be brought up and down by the master during scaling. Note the following points about the Kubernetes architecture. 1. Nodes are managed by the master system. Each node in the cluster must have a container runtime, such as Docker. 2. A given node can host multiple pods. 3. The pods, a logical group of containers, are running independent modules of an application. In my last article, It was a single container running a module. 4. The pods are replicated across multiple nodes. 5. This architecture mitigates the chances of a single point of failure, and thus provides high availability. The master system brings a layer of abstraction to the external client/application. Service and volumes. All pods that are running the same application module share storage resources. Further, all the containers within a pod share the namespaces and file system volumes. Hence, in order to have a persistent way to store data, volumes can be attached to pods. Whereas, in order to have a persistent way to communicate with ephemeral pods, a higher-level service abstraction is provided, called Kubernetes service. Note, service is an abstraction of a set of pods and an interface for how to interact with the pods. How do you set up a Kubernetes cluster? There are two main methods. 1. Set up a local cluster, preferably with Docker Desktop. If you are using Docker and have enabled Kubernetes, then you already have a standalone Kubernetes server running. 2. Provision of a cloud cluster. Most cloud service providers offer a managed Kubernetes service. Amazon through Amazon EKS. Google through Google Kubernetes Engine GKE. Microsoft through Azure Kubernetes Service, AKS. In this article, you will learn to use Amazon EKS. You can consider a cluster as a collection of worker nodes, virtual machines. These nodes run the containerized applications. A cluster must have at least one worker node. Each worker node hosts the pods, where a pod is a logical group of running containers. A master system. This system manages the overall cluster. It manages load balancing, backup, replication, scheduling, and much more. The master system is actually a control plane comprising a few components. What is a control plane? The control plane manages the worker nodes and the pods in the cluster. For example, it decides when to start up a new pod, or schedule other events. It comprises the following components. 1. Kube API server. This is the core component. It is an API server that exposes the Kubernetes API. In simple words, the Kube API server is the front end for the control plane. It has two main purposes. It exposes an HTTP API that allows end users, different parts of your cluster, and external components to communicate. It allows querying and manipulating the state of API objects, pods, namespaces, config maps, and events. 2. It is a key value store of the cluster data. 3. Kube scheduler. It monitors pods. It assigns a worker node to the newly created pods. 4. Kube controller manager. It is an abstract layer that runs controller processes. 5. Cloud controller manager. It embeds cloud-specific control logic and lets you link your cluster into your cloud provider's API. What's there in a worker node? A worker node comprises the following. 1. Kubelet. There should be an agent on each node that tracks that containers are running in the correct pod. That agent is a kubelet. 2. Kube proxy. It maintains network rules on nodes. These network rules allow network communication to your pods from network sessions inside or outside of your cluster. 3. Container runtime. Of course, each worker node needs a container runtime, such as Docker, Contained, CRIO, or any other to run the containers. Conclusion. In this part 1 of the article, we have learned some fundamentals and key concepts like container orchestration, container scaling, and Kubernetes. Next, in part 2 of the article, I will work with you through creating the clusters and tools needed to successfully deploy a cluster to Amazon EKS. Stay close.